can start? Okay. All right. Hey, everyone. My name is Shin, and I'm on the research team at Uniswap Labs. And today I'll explain the new feature of Unichain, which is a rollup that we're building, and the economic implication of this feature. It's called Revert protection. Most of the results, or all of the results that I'm going to present, are included in this paper called Quantifying the Value of Revert Protection. You can find this paper on arXiv. So if you're curious to read through the proof or just to reference, you can find it online. So just for context, I think people are familiar with Revert, but to be explicit, it means when your transaction failed to execute on chain and it failed halfway through the execution, you as the user still have to pay some non-zero cost. And revert protection simply means that you are protected from this cost, and it usually is implemented at the block builder or the sequencer level, where this party would simulate your transaction and they would exclude it from the block if it sees that your transaction would fail in simulation. So essentially your transaction disappears instead of revert in a block. Now, you can do this in different settings. The setting that most people are familiar with is the mainnet sort of bundle auction setting, where searchers submit a bundle of transactions to the builder, and the builder, out of a handshake agreement, simulates these bundles, and in the case of a revert, they exclude the transaction. The second setting, which is what we're modeling today, is a setting in which the layer 2 sequencer commits to providing this service to its users. And the commitment can be, again, in a handshake as it occurs in the L1 setting, or it can be done a little bit differently as we're trying to do for Unichain, which is in a TEE. But regardless, the economic concept is the same, which is we simulate your transaction, and if it fails, we exclude it from the block. So you can find this table in our paper, and it summarizes different settings across different sort of chains and ordering rules and how this model could apply. And note that in our analysis, the degree of revert protection is parameterized by two different parameters, R1 and R2. And they simply express the cost of revert as a fraction of a successful transaction. So if you set both R's to 0, it means you're fully protected. If you set them to whatever value they occur on L1, it means there's no revert protection. So we don't express it as a binary outcome, but rather as a continuous spectrum. So when I was first informed of this potential design, I was intrigued because in my mind it goes like this. We have developers who are building Unichain, and they're like, oh, you don't have to pay for reverted protections ever. And in my head, I was like, are we just giving up money that we could have made? But it turns out to be not the case. And I want to convince you why that's true, even if everyone is sort of behaving rationally. So in our model, we have end users, and you can think of these users as arbitragers. So we're not modeling a retail user here. We're just modeling someone who is trying to make as much money as they can. And what they do is they arrive at the chain and they observe a common value V. So everyone agrees that there's an opportunity of value V that they can capture, but only one of them can capture, 1 out of n. And then they can join this auction. And here it's important to mention that Unichain is following priority ordering rules. So within each block, the ordering of the transactions is basically whoever pays the highest priority fee gets the highest place in the block. So here the user has a couple of things they can choose. They can choose whether to join this auction. So when they see an opportunity of value V, they can wave their hand and say that it's too small, I'm not going to bother. Or they can decide to join. Once they join, they must pay a base fee. So the base fee is non-negotiable, conditional on them joining. But they can also choose a priority fee. And that priority fee, in the context of other people's priority fees, determines their position in the block. And because we're modeling a sex-to-X arbitrage, whoever has the first position out of this n users will get that opportunity, will get that V, and everyone else will pay a revert cost. And that revert cost is basically the cost of participation, and the V is the reward. So as an example, on mainnet, if you have a reverted transaction, usually you pay between 10 and 20% of an otherwise successful transaction. So you can interpret this as R1, R2 being set at between 0.1 and 0.2. So yeah, this is a strategy space. We show that there doesn't exist a so-called static strategy. So they can't, what that means is they can't close their eyes and say, I will always participate, or I will always participate with a fixed bid. What they must do is they must first randomize between participate or not participate, or participating or not participating. And condition on participating, they also have to randomize their priority fee. So they can't have a strategy that goes, I'm going to participate with 50% probability, but if I participate, I always bid V or half V or something. They have to randomize their bid so that other people can't react to their fixed strategy. But anyways, I will skip over most of the derivation and get to the results because I think those are more interesting. So basically, in an equilibrium, in a mixed strategy equilibrium, the players must be indifferent between different strategies because if they prefer one over the other, they can just throw away the one that's dominated. So in here, they must their payoff, because it's competitive, it must be 0, and that's the first condition. And then you can solve for the free parameters that they're choosing, which is the chance of participating, and then this like cumulative distribution of their priority fee conditional on participation. Okay, results. So I want you to first only stare at the left graph. And the x-axis is R1. So that is the fraction of the base fee you have to pay if you revert. It goes from 0 to 1. So it goes from you don't have to pay any base fee to you have to pay the full base fee. And then the y-axis is the expected auction revenue. So just focus on the direction of the lines. What this chart says is, according to this model, as you offer more and more revert protection, which is moving the x-axis to the left, because R1, when R1 gets smaller, you pay a less fraction, that's more protection. The sequencer would generate higher and higher revenue from arbitrageurs. Well, that's good for us because we are offering revert protection and we are making sequencing fees. So it's good news in the sense that we are not doing this thing out of altruism, but rather we're incentive aligned. And then the second thing I want you to look at is now the right graph. So it's the same x-axis, but the y-axis is now the expected number of transactions submitted given an opportunity. And you can see that here we run into some problems because if you offer full revert protection, then you expect everyone to always participate. And that creates somewhat of a spamming problem that we'll deal with later on. So right now I'm going to do an extremely big hand wave and say, don't worry about it. Let's worry about the left side first. So I want to highlight, I guess, a couple of things. One is you don't have to look at the formulas, but just look at the first line. The total revenue collected by the sequencer can be split into two components. That's the fee we make from base fee and the fee we make from priority fees. And it turns out that we can think about these two separately, which is good. And if you look at all of these expressions, there's no R2 in it, which means the degree of revert protection we offer on the priority fee has no impact on the expected sequencer revenue. Now that might seem pretty convoluted to think about, but I'll just note that there is a mechanism that we're using right now on Unichain called MEV tax. It's a mechanism design proposed first by Paradigm, and we're using it right now for order auctions, but later on might be for other things. And that mechanism essentially is just tweaking this R2 parameter. And so what this shows is whatever we do on the R2 side, it doesn't affect the total amount of revenue we collect from this auction. It only affects the distribution of that auction revenue. And we can discuss more about that later. The second result is auction revenue decreases monotonically in R1. And that means we want R1 to be as low as possible, and in our case, 0. And let me just explain. Maybe I have too many words here, but let me explain the intuition. So the intuition, and you don't have to look at this, you can just listen to me. The intuition is because there is only one common value V, and that will be how much value there is for everyone to share. And now, because the arbitrageurs are competitive, in the long term, you can expect their competitive environment to give them a profit of 0. So that means whatever value is being auctioned will be passed on to whoever is running the auction, which is the sequencer. Now, when would the value not realize? That will be when nobody is participating. So the result says that if you want to maximize revenue as the auctioneer, you want to maximize participation. And in our model, participation is basically affected by the cost of a failed participation. If you make that 0, everyone will always participate. And that's how you maximize auction revenue. Okay. One other note I want to mention is even though you have the spamming problem, as we mentioned, but in the case of infinite amount of participants, you still have a finite limit for the revenue, and that's because as the number of participants grew, they will choose a strategy that's less aggressive, and that effect offsets the increase in number of participants, and your expected revenue converge to a finite amount. And I think block space and mempool usage is something that's heavily affected by the expected number of transactions submitted. And here, we basically show that mempool usage is what we need to worry about as we offer stronger and stronger revert protection, but it has the upside of saving block space for other usage. Okay, so now we go back to that big hand wave that I did, which is I was offering completely free revert protection, and that means as the number of participants go to infinity, so does the expected number of transactions. What are the things we can do to realistically handle that problem? So one way to think about it is to think of the cost of offering this service on behalf of the sequencer. And so what does it take us to offer that service? For every transaction that we would consider including, we have to simulate it. And we can think of that as kind of a small computational cost. And we can call that C per transaction. Now, knowing that there is a C, the sequencer, as the designer of the policy, can choose one of two actions. The first action is to internalize that cost. So the sequencer would basically plug C into all the math that we just did and say, now solve for the best R1 and R2, given there's a C for every transaction submitted. The second course of action is to pass that cost directly to users and let the users decide what their strategy should be given the C. And this extension tries to find out which course of action is more efficient. So the first one is we as the sequencer tell the user, hey, don't worry, just submit your transaction and I'll tell you the R1, R2, but no extra cost for revert protection after that. So you can think of it as like a partial revert protection, meaning reverts on Unichain will look just like reverts on other chains, but a lot cheaper as a percentage of the total gas. And the second will look like more like a pay-as-you-go service. So every time you submit to this revert protected endpoint, you would pay a flat fee. And after you pay the flat fee, that service is offered to you completely, and that's it. Which one's better? In this model where there's only sex-sex arbitrageurs, the result is intuitively the first one, when we internalize, both R1 and R2 will have a non-zero optimal value, meaning we would never be able to offer full revert protection when we don't pass on the cost. Otherwise, we'll have a basically expected amount of submitted transactions going to infinity. Under scheme 2, you would want R1, R2 go to 0. And what that C does is it essentially creates some kind of a floor where and people participate much less, and the expected number of transactions are bounded. Or rather, sorry. In the case that it's not bounded, we can still afford the cost. 1 minute? Yep. Okay. To simulate those transactions. So the implications are we must first think about how we're going to communicate up with our users and then solve the best R1, R2 under those. And since everyone is here, I just want to encourage you to think about where all these hypotheses and conditions we have set out to assume, do they hold? And does any of these features help the outcome metric that we want to achieve? And so these are just questions, so I'll skip them. That's it. Thanks, everyone.